Everybody hear me? All good? Yeah? Cool. Well, thanks for having me here. And to start off the evening, talking about a Mars habitat that we designed. Maybe a little bit of background information first. I work for Hassell Studio. We are a fairly large international architecture, interior design, and landscape architecture firm. Originally started in Australia many years ago. Now we're also operating from Asia. We have a London studio with about 60 people. And a couple of years ago, we also started a San Francisco studio. Our work is quite a variety of work, from small interiors to big infrastructure projects, museums, interiors, and so forth. So it's quite a wide range of projects. Myself, I am the head of design, technology, and innovation at Hassell, and that's a global role. So I do that for the whole practice for all of the studios. This is a little snapshot of kind of what my world looks like on a day-to-day. Under my remit is anything to do with design technology, and that can be anything with BIM, anything with visualization, computational design, digital fabrication, and even physical model making. I think it's all part of that one spectrum of design technologies. And we also do innovation, which means we often work on, now and then actually, we work on very special projects. And today, really, I'm going to talk about that, about one of those very special projects, which is this one. It's a Mars habitat that we designed for NASA, and this was part of NASA's Centennial Challenge. Now, Centennial Challenges at NASA are ways to bring in industries that normally don't really get involved in space, such as architects, for example. So we were very keen to join that. That's about almost 2 years ago that we joined it, finished it just over a year ago. Now, once you get a project like that, a brief like that, how to design something for Mars, for those first humans to settle in Mars, where do you start, right? Well, as an architect, you often sometimes say, well, look at precedents, right? So what are our precedents? Well, this is a precedent. This is the largest space habitat out there for the moment, International Space Station. It's an interesting one, but the moment you start looking at it on the inside, it looks all very engineering, right? And there's well, it's hard to think there are any designers or architects involved in organizing this space. And you're right, there are very few architects involved. What you get is a very much engineering systems where humans are just another system. I would say another kind of operating another system within this big machine. We're really part of the machine. So maybe not a good example to start to think about a space where you want to live for a long time. So of course, when you think about designing for space, the first thing that comes up, of course, is sci-fi. And it's very tempting to go and say, well, let's look at sci-fi images. Let's browse the net and kind of think about all those great shows and great movies from the past: Star Trek, Space Odyssey, amazing interiors, Alien, and one of my favorite ones, Moon. But let's not forget, these things are really stage design. This is science fiction. What we're trying to do is really science fact. So looking at references from science fiction was not really the right thing to do. So what we try to do is look at other references. For example, look at other architects that might have worked in space for real. One is this woman here, Galina Balachova. She was the only architect, the only woman architect, actually the only architect to work for the Soviet space program. And she was involved for many years, to design the interiors. This is one of the interiors she designed. This was for Soyuz orbital module. And I just love these little drawings because they really show something very different to what we see in the ISS. You know, you see some wooden veneers, you see some fabrics, you see some pictures. You know, it looks very homey. It looks almost something where you would want to live in. She also worked on this. This was actually exhibited in the Science Museum in London a few years ago. This is the Russian lunar lander. An amazing looking machine, I think, that never landed on the moon, of course. The Apollo missions were first, and the Russians actually, in the end, were never achieved to do that. And look at the machine, and then look at the interior drawings of what she's done. I just love how kind of normal and almost non-technological they are, and non-machine-like they are. So I think there's something to learn from her. She also works on the Mir space station, where she did some of the interiors as well. Just look at these drawings, just amazing work, I think. Now, another person we looked at to get inspiration from is Raymond Loewy. Raymond Loewy, a famous industrial designer, American industrial designer. He got involved in NASA quite a bit, and he was really the first designer to be involved in any of the programs at NASA. Now, the big project that he got involved in was Skylab. Skylab was one of the first orbital space stations for NASA. And they brought him in, and just another kind of wonderful drawing by Raymond Loewy. And the space engineers, were a bit skeptical. So, what is the designer going to do, right? Is he going to choose the color or something like that? What is he going to do here? But he did indeed choose the color, but he did many other things as well. And you see the most important thing that he'd done, you can see here on this image. 3 astronauts in Skylab. First thing he did is he gave each of the astronauts a private space, right? The engineers that designed Skylab did not think the astronauts needed their own space. Imagine being in the same capsule, because there was only one major capsule, with all the other astronauts the whole time for weeks and months at a time. So he gave them their own little space. Second thing he did is design the table. You might think, well, what's so special about this table? Well, originally, the engineers did not design a table. There was only little kind of trays that flapped out of the sides of the space habitat on the inside, of course, and you could sit there and eat, and you were not actually facing the other astronauts. Imagine that, having to not be able to have a meal and have a conversation about what you did that day. Right. So he did that. He actually designed it, but he actually made sure there was a table. The third thing he did, which I think is absolutely extraordinary, is that he did the window, and you can see it in the background, the little window. Now, that in the original design, again, the engineers did not think it was necessary to have a window. So imagine, as a Skylab astronaut, going hundreds and hundreds of times around Earth for weeks and months, and then never be able to see this, right? Extraordinary. So, learned quite a bit from that, I thought. Now, this is kind of like precedence. So once you kind of start designing for Mars, what are we going to do? Well, I think instead of kind of looking at references, what we really want to do is look at first principles and understand what is the environment there. What are we really, really dealing with? First thing to do is see where it is. This is a picture, the famous Earthrise picture. It's a picture from taken from moon orbit towards Earth. Now, if you do the same picture from Mars, this is a picture taken from the Curiosity rover. Looking back at Earth is just literally 1 pixel on this image. Now, the distance from Earth to Mars is about 1,000 times the distance from Earth to the moon. So it's extremely far, which means that it's extremely expensive, whatever you take there. So the trick is to travel really light and to travel really compact. Remember that, light and compact. We go to Mars. Other things that are interesting about Mars. You have weather, you have an atmosphere, you have storms. You actually have sandstorms that can last months and are completely planetary. So you have storms that completely go over the whole Mars planet. Another thing, now Earth has this fantastic thing that we have magnetic poles. Magnetic poles actually help Earth to protect itself from radiation. Radiation from the sun, radiation from the cosmos. It's a really important thing. Because on Mars, we do not have that, which is a bit of an issue because we get really high radiation exposure for the astronauts. And this is really the main thing that our astronauts will have to protect themselves, is from this really harmful gamma radiations. So Mars, what else is there, right? Well, we have an atmosphere. It's a very thin atmosphere. It's mainly CO2. It's really cold. It's often roughly around minus 70 degrees Celsius. The hottest it ever gets is, I think, about 10 or 20 degrees. So it's really cold, thin atmosphere. Oh, and it's a third of the gravity on Earth. So that's kind of what we have. Now, our design is really based around the following concept. It's based around two things. The internal pod, which you just see a kind of like lovely inflating and unfolding. It's a lightweight system. It's made on Earth and it's brought with the astronauts to Mars, where it actually inflates itself. It also holds the pressurized volume. It holds the atmosphere, the oxygen for the astronauts to breathe. On the outside of that, we have a big shell. You see this brown thing, this big mass. That really is there to protect the astronauts from radiation. The best thing really would be to live in caves, right, as an astronaut, because you need mass to really protect yourself from the radiation. Now, remember what I said. We need to travel light and compact. We're not going to bring masses of concrete, of course, with us. So we'll have to do something else. What we're going to have to do is use local materials. There's not much that we have there. But the only thing we have is regolith. And regolith is what we call Martian dust, really, right? And there's lots of that. And what we're going to do with that? Well, we're going to use that to 3D print a shell structure under which our own kind of self-made cave to live under. And as you see, we have all these little kind of almost ants 3D printing this. These are small, fairly small robots, because of course we're not going to bring a massive 3D printer with us. That would be a bit ridiculous. And as you can see, these are our robots. 4 types of robots. One finds the regolith. The second one digs it up. The third one brings it to the side. And the fourth one is actually binding it together through microwave technology. Now, let's talk a little bit about how the habitat is built up. Of course, on top, we have the big shell structure, protects ourselves from the radiation. Underneath, we don't just have one of these bubbles, these pressurized bubbles, inflatables. We have 6 of them, and they're all connected with a connector pod. And as you see, each of these connector pods then becomes either suit ports, which are ports where the suits are on, or it can be an airlock, or the third thing it can be is a connector to the rover, the Martian rover. Each of these pods are quite similar, right? They all have a kind of a radial grid, and they all kind of have the same topology. But they're all quite different. We have one of them is our living quarters on the bottom here that go around anti-clockwise. We have our the gym plus the private rooms. We have a small bedroom, each of the astronauts. We go up, we have our lab, we have a greenhouse, we have a workshop, because it's really important to be able to fix stuff. And then we have storage space as well. Now, you can kind of see that the whole thing is really built out of these racks, these radial racks, and they can all be something different, right? They can be storage, they can be a room, they can be a kitchen unit, and so forth. Now, that system is something that we kind of developed ourselves, because we thought the way the ISS is built up is spatially not that great, right? ISS is built out of these kind of big cylindrical volumes, where typically you have storage on the bottom and the top. They still have bottom and top. And on the side, you have these racks, which are science racks, right? But those aren't used all the time, right? It might be that an experiment is set off and then an astronaut leaves it for maybe a day or hours or so forth. So in the end, with this kind of topology, what you get is lots of corridors with science racks. So we thought it could be much better if we find a system where we have a radial system that with racks that really could open up and close. And you can kind of see that here. This is our science module, the lab module, where you see astronaut there doing some work. He could then actually open it up and get into another one. It's very similar to what you could find in library archives, you know, this big kind of shelf that you can move around. Very similar to that. And a shelf could also be maybe a greenhouse shelf where you grow some plants. So it's the same setup, but the infills are each time slightly different. And here, the same thing. This is a gym and also the private rooms. Now, what I really want to do today is, it's a little bit different from how I normally do this talk. I really want to talk about all the visual artists and designers that really were involved. So anybody that had anything to do that as a visual impact of the project, I want to talk today about that today. The biggest one, the biggest collaborator of the project was, of course, Lightfield, but you will hear all about that from James and Clark after this talk. So I'm not really going to talk about Lightfield too much, because they have their own half hour to explain how they actually created the video that had to be produced for this project. But I'm going to talk first about a few other collaborators and how we kind of worked on getting this kind of overall view that we really set out to do, how we could create that overall vision. For renderings, we worked with Agnet from Imigo on these images, and what we really try to do is really get some of the spirit of Bolachova in here, and using some different materials. So as you see, we used some bamboo veneers, right? Why not create more tactile materials that you would have in your living room, right? So, and you might even need to take them with you. You could potentially grow them on Mars as well. You can see in the background, there's some bamboos being grown. The second thing important in this image, of course, the view, right? Being able to create a large view out, learned our lessons from Skylab, not just to the Martian environment, but also to the rest of the habitat. Being able to see another person that's not in your own space. I think that's actually quite an important thing to be able to do when you're going to live there for more than 3 years. In this image, you really see, I think, we really wanted to show is that it's a nice place to live, right? It doesn't have to be hardship. As an astronaut, you don't just need to survive. I think we need to thrive on a different planet. Now, there's a really interesting detail I want to talk about. Is you see in the front right-hand side, that are those robots that were 3D printing our shell structure, right? And Agnet did this thing. She said, well, you know, once you're finished with the robots, they have nothing else to do. So they made this kind of heap of, you know, discarded robots, bit of a boneyard of robots. Although I really love the image and the idea of the discarded robots, it was a bit shocking for me, because we're going to go to Mars, and then the first thing we do is create a dump of robots. You know, we have to, when we go to Mars, we have to think about it in a completely different way. We have to really think about sustainability in a completely different way. And we need to think about reusing and recycling everything we have. So we actually went back to the drawing board and we redesigned these robots. They're not 4 types of robots anymore. They are a system of robots. It's a Lego system of robots. You have different blocks that then can create different types. One wheel together with a battery pack might become the robot scouter, the scouter for Regolith. Add a few more wheels and a few diggers, and it becomes your Regolith digger. Add more batteries, more wheels, and a printing head, and then maybe it becomes your printing system. So really that idea of recycling and reusing, being much more resilient with a system, we try to bring into every aspect of the design. We worked with Agnet through Bluescape, which was kind of our online pinup board, where we're able to kind of do markups. So we use that with the guys from Lightfield as well. I think you guys will show that later. As you see here, the markups and the reference we use, we did again not really use references for space. We really used at workshop references, what a workshop looks like on Earth. I think that was really important to keep it really science fact and not science fiction. And this is that workshop that we have. It's a lot of detail in here, and there's actually a few, all the parts in here really tell a story, and there's two stories I can tell about this. The left-hand side on the background, that's a 3D printer, a Delta 3D printer, printing some big parts, and I'll explain that in a minute. On the right-hand side, you see a sewing machine, right? And you might wonder, like, why do we need a sewing machine on Mars? Well, think about recycling and reusing to the extreme. And what if we would reuse the parachutes that we landed on Mars with? You know, Mars will use, landing on Mars potentially use parachutes. So why not reuse that material for something else? Why not use that to make the clothes for the astronauts? Now, the great thing is I knew of a guy that exactly did that, and that's Chris Rayburn. Rayburn started his label in Hackney many years ago, and that's what he does. He is really extreme in looking at how we can reuse materials. And one of the things he does is really he makes clothes from used parachutes. So I actually didn't know him before this project. I basically called up, went to their store in Hackney, walked in, talked about I'm an architect and I'm designing a habitat on Mars, and somehow they listened to me. And about a day later, I was able to come back, and Chris was super nice and allowed us to use all of the garments they had in their archive to really use for our photo shoots, for our green screening, for the images. So yeah, super nice of him. That was, you know, not knowing us, and then be able to kind of give one of their archive pieces for the shoots. And our collaboration continued then, really, because afterwards, and when we continued the development of the project, he really got inspired by our design, and his 2020 spring summer collection was based around Mars and our Mars habitat. And that's it. That's one of the pieces they made. It's made out of blankets, emergency blankets. These pieces. Other pieces have prints of high-resolution NASA prints from Mars. And other pieces are then made out of the parachute material as well. And you know, and of course it's a great thing to get a fashion designer involved, because then you kind of, you know, they make them t-shirts with your own design on, right? So that was a lot of fun to kind of get him involved. The second thing we did, and remember that kind of interior shot I showed, we had these big sofas, right? These big chairs and all that. For that, really, we worked together with Manuel Jimenez Garcia, a good friend of mine. He's also an architect, and he has a company called Nagami, and that's a furniture design and fabricator. He's based just outside Madrid, and this is his factory. He actually has a larger factory now. This was a factory he had last year. He expanded, and you see all the furniture in the background, all designed, some of the pieces designed by himself, and 3D printed by these large industrial robots. Now, and he designed all the furniture for the habitat. Right? You might think, well, isn't that a bit crazy? You told us in the beginning that we need to pack light and compact, and we're going to bring these big 3D printed pieces. Well, the thing is, of course, we're not going to bring them. We're going to print them there, and we're going to use waste material. What we're planning to do is use recycled plastics from science experiments and from food packaging. So there will be waste. So why not reuse it to create the furniture that we will be using? And it didn't just stay as renderings. Of course, we did it for real. So this is Manuel printing one of those air chairs, they're called. You can actually buy them now as well. If you go to nagami.com, you can see them there. Printed in one go over a few hours in one thin shell of plastic. Now, and you might think, well, Xavier, you kind of made them look very spacey, right? Yet in the end, they looked very spacey and they looked very transparent. But we didn't actually plan out to set out to do that. The transparency is because of reusing the recycled plastics also here. And the design of it is this kind of one smooth curve because we have one continuous printing profile. A continuous robot can continuously keep on printing, and that gives us the most efficient shape and fabrication method. And you can see that here, one of the finished products. And just to prove you that this is not a rendering, it's not rendering, we have a person in there. So it's really just kind of floating one piece of plastic, of recycled plastics. Another thing we did is we worked with Juan. Juan used to work for us as well, but then he kept on working on this particular project. He's an architect, and we got him involved to do some drawings, right? Drawings for what? Well, for this project, I kept on saying this is not science fiction, it's a science fact. To make it really fact, we collaborated with Cranfield University and together with the students of Professor David Cullen. Now, he has a master unit that he teaches, and the students are all space engineers. And what they did is they helped us with looking at two things. First, looking at the system engineering, looking at how much energy we need, how we can get the energy, how much water we need, how we're going to recycle it. So they were always there to always fact check whatever we were designing, that it would actually be a good proposition. The other thing they did, they looked at the mission architecture. The mission architecture is really looking at how we get stuff there. The most important thing, how are we going to get our habitats on Mars? And you might have seen kind of these graphics, right? These graphics that you have from NASA or from ESA, looking at the mission architecture. I think this is the Apollo one, looking at how, getting into lower orbit, which bit comes off, which bit turns, which bit then lands. It's quite a complicated dance of different maneuvers. So there's kind of the graphic explaining how stuff gets there. But on the other hand, I also want to show the architecture. And I got a bit of obsession with future systems, and particularly this book showing Jan Kapliczky drawings and drawings of his design. And I really love how clear and minimal they are. They're just line drawings, and I still love line drawing as well. So I gave this book to Juan. I said, I know this is kind of what we're after. We want something like this, but also mission architecture. And then he came up with these two drawings. The drawing on the right-hand side, you've seen part of it already, really explains the architecture, what will be there, how all the bits come together. But on the left-hand side, we really have the mission architecture, explaining in a very graphical way how we would get all our bits to Mars. And that's really why we needed a visual artist for, because of course the Cranfield engineering students, they had all the numbers and all the spreadsheets, but you couldn't present it in an interesting way. So we kind of asked Juan to do these two panels for us to really encapsulate the whole project in these two drawings. And one of the submission materials we had to do for NASA was a model, was a physical model. I went back to one of my old colleagues from Foster's, Sam Morgan, who's at Base Models now in Battersea. And well, the great thing is that whenever you come with a space project, everybody really gets excited, which is a good thing. They also got immediately excited about this project. It was great working with them because, we already had some of the renderings done by that stage. And what we really want to do is make sure this was going to be a presentation model. This was going to be a model. This was not a design development model. This was not going to be an abstract model. What we really want to do is get as much detail as we could in there. You kind of see that some of the details here, all these kind of etched little science racks in there, all detailed to like minuscule detail. It was a combination of really interesting techniques. We used milling, laser casting, etching, 3D printing with different kind of techniques, vac forming. I think every kind of interesting model technique came actually together in this project. It's quite a difficult project to present because most of the habitats are kind of stuck underneath that kind of regolith shell. So we decided only to do half of it and then open it all up so you could almost play with it. You know, you could take all the hoods off of all these little habitat pods. And then we were really, really lucky that we got invited by the Design Museum to become part of their Moving to Mars exhibition. That happened all just before COVID started. I think the exhibition was finished in February last year, so I hope some of you saw it. It's now moved to Stockholm, where it is in the Science Museum, and hopefully in a few months it will open there. The Design Museum asked us to go and build one of our pods. So we're super excited because now we didn't just have a design anymore, we had to get some construction drawings out as well. And we wanted to capture that in the right way. For that, we worked with NARA architectural photographers that we know. They often kind of take pictures of more kind of experimental pavilions and architecture, and you know, they were absolutely the perfect fit for that. The great thing is they were actually able to come twice because we had a bit of an issue. The big pod, the inflatable pod that we designed, was a few weeks late. So these are the pictures without the pod. But what you do see is that we created this huge wall, this video wall, that we could have this continuous view onto the rest of our habitat. There's some work that the guys from Lightfield also did, but I think they'll explain that in a bit more detail. And in the front, of course, the furniture designed by Nagami. And then a few weeks later, we got a pod, our inflatable pod arrived from Ljubljana, and we could have Nara over again to take the final shots of this project. And as you see, what we really try to do is to create a space where you would really want to stay, where you would really want to live, but at the same time is super, super practical. As you see these kind of shelving system, that the racks that could open up and radially move. You could open it up, go in, do an experiment, come out again, do something else. So try to almost kind of test it out, have a prototype how that could work in real life as well. Have a little nap there in the Nagami chair. And so this is the kind of final shot of the project. Again, using different types of materials and just creating a space that we believe would be great to live in. I'm gonna finish it there, and I think what I would finish with is probably the video that the guys from Lightfield created. And if we play that now, it's about 5 minutes, and I think, Josh, are we gonna have a break then? And then Clark and James will talk about the video?
I think we could move straight into
okay, cool.
Clark and James' presentation. Yeah.
Should I stop sharing and then you guys play the video?
I think perhaps if you'd like to finish up, we might take a few minutes for questions. Should we do that before the film, Xavier?
Yeah, I got a couple of questions.
Go for it, Simon.
Xavier, thank you. That was an incredible presentation.
Thank you.
Really, really good. Apologies for the interruption halfway through, but there you go. Never mind. It was nice to see that Naro were involved. They really talented company, and we did a photography workshop with them at HB a couple of years ago. It was really cool. Also, I had a question about you showed a beautiful book about halfway through as a reference for line drawings, and I wondered if you could just repeat what that was, because I missed it.
Yeah, it's a book. I think it was part of an exhibition. It's called Jan Kipliczki Drawings.
You're gonna have to spell that to me in the chat.
Oh, I don't know.
And then I'll put it in the YouTube comments.
So he was one of the founders of Future Systems, right?
Okay, cool. Oh, okay, got you. Yeah.
And it's kind of interesting. a co-founder of Future Systems, actually David Nixon, who ended up becoming a prominent space architect. He actually worked after he left Future Systems, I think he was there for 10 years. Then he left, he moved to the West Coast, and one of his major clients was NASA. He was involved in some bits of the ISS, but what he did do, he made a beautiful book on the ISS. It's called The Architecture of the ISS. It's a great book to read, great piece, looking really at it from historical, but also from an architectural perspective.
Yeah, I mean, I love renders. It's my job, obviously, but I've always got a massive soft spot for line drawings. They're always really, they just suck you in like nothing else can, I think. Anyone else? Anyone have questions? Anyone else?
Yeah, I have a question. Actually, Xavier, I really like your presentation. Thank you. That was amazing. I like this science fact statement that you made. I'm interested. How long does it take once the Martians get there? Once the astronauts get to Mars, how long before they have something inflated that they can get into and be protected from the environment?
You'll see that in the video, actually. But we think, I need to kind of look at the thing again, but the inflatables will be done by the astronauts. So the habitat is, the shell is 3D printed first. Once that is done, the astronauts will arrive. But it should be fairly easy to inflate. So we're thinking it'd probably only take a few days to kind of set up the whole habitat. So once they inflate it, they can then start building up everything from the inside.
Right.
Louis in the YouTube comments has a good question, and he's asked about menu fatigue. And can he ask about catering and kitchen on the mission?
I have a good one about that. So I talked a lot about kind of tactile materials, right? That's something we also kind of knew from the people that live in the Antarctic. I know the kind of I think he's now head of polar operations, John Eager, and he used to be the commander of the Halley 6 base on the Antarctic for the winterization crew. And I had long conversations with him, and he kept on telling me that they missed tactile stuff, being wood, warm materials, for example, in their habitats on the South Pole, but also tactile stuff to eat. And he said, what we did is that we grew, for example, lettuce, not because we needed it for nutritional reasons, but because we wanted something crunchy, right? And if you see what we have a greenhouse. The idea is that we think the astronauts would be growing stuff for them to eat, but not to actually completely have their whole menu taken from that greenhouse. That would actually not be possible for many, many years. So they would bring pre-prepared food from Earth, but they would actually supplement that with stuff that they would start growing on Mars.
Cool. Just interesting because you mentioned the South Pole scientists stuck out there. I read last week that the day after the last plane flies out of the base, they all get together and they watch The Thing, because they know they've got another 4 months before there's any outside contact, which I thought was quite good of them.
It is the best, are the best analogs, those bases, because there is no way in or out. If somebody needs medical attention, it will happen with that one doctor that is on the base. That's it. That's your only shot. There's no way. You can't really get evacuated in the winter from these bases. You can get evacuated from this National Space Station in about a day, no problem. But those Antarctic bases are very tough.
And Xavier, I think I've got one more question from the YouTube comments, and then we'll move on. But Sam asks, how do you feel like designing for Mars and space will inform what life is like on Earth? Obviously, sustainability is a hot topic right now, but do you think anything else will feed back?
Well, I think sustainability was a really big one. It was actually for me personally as well, because I was always kind of, designing around it, but it was suddenly for me designing with sustainability in mind, but once we did this, it really showed us it's life and death. You know, it's not a nice thing to have. It's not a tick in the box of BREEAM or LEED or whatever these things are. It was, you really had to think about it really, really hard. That because the only thing they have, these astronauts, is what they brought and what is there, and there's not much there. So yeah, for me, sustainability is really a really big one. The other thing which I'm always kind of intrigued by is how the ISS is still very much divided in different bits according to geographies. You know, the Russians have that part. There's a European module. There's the American module, and although they all kind of live together, they all kind of hang out often in their own sides. So I was wondering, once we kind of move to Mars, can they just call themselves Martians and hopefully forget about the geopolitical backgrounds that they all come?
That would be nice, yeah.
Yeah, you know.
Okay, I'm going to hand over. Thank you, Xavier. Fantastic, really, really fantastic. Thank you so much. I'm going to hand over to Josh, and he will introduce the next speakers. Thank you.
Yeah, before we move on, Xavier, could you stop sharing, please? Actually, just so that we get the interview back up. I've got a couple of questions as well. Is it true that Mars is also flat?
Well, you can read all these things in our. You know, if you look at a video in the YouTube, we have a lot of flat earthers doing comments. It's quite neat.
What my question is, can you tell us a little bit about how the project has been received generally by the public, and what sort of challenges you faced from any kind of backlash or from?
Yeah, it's, well, the one comment we always get is, well, why do you think about going to Mars? Well, there's so many problems still on Earth.
Yes.
Why do you do that? There's a one thing that always comes up. And why would we all want to move to Mars? And to be honest, I don't really want to move to Mars, right? It's a pretty extreme environment to live in. It's going to be pretty harsh. And I just want to kind of put the analogy again back to Antarctica. You know, in Antarctica, we are there for science. Nobody's going to go and live there. We protect Antarctica very thoroughly. You know, you can't have a cigarette butt and drop it in Antarctica. That's highly, highly illegal, right? So I think we'll treat Mars like we'll treat Antarctica. But honestly, I do not believe that we should use, such as Elon Musk says, that we should all move to Mars and to have like a second backup planet. I don't really believe that.
Great, excellent. Unless there's any other questions, I think what we'll do is introduce our next presenters and play the film, which Xavier mentioned before. We're now going to hear from Clark Denman and James Lehman, the founders of Lightfield. First of all, we're going to watch their beautiful film. Thank you.
Half a century ago, we took our first step on the surface of the moon. Today, there is renewed passion to explore for our next human endeavor. Mars, the red planet, further than any human has ever been. We face many challenges: remoteness, no livable atmosphere, high radiation, dust storms, and extremely low temperatures. Before any humans set foot on Mars, we must first design a protective shelter. We will protect our astronauts from radiation with a thick 3D printed shell structure using Martian regolith, which works great in compression but does not perform well under tension. To overcome this shortfall, we have chosen to construct the pressure-retaining parts of the habitat from lightweight, inflatable pods. They will be made out of high-precision engineered composites that are prefabricated on Earth. Their elliptoid geometry will be able to mitigate the pressure differences whilst optimizing spatial planning. To create the base on Mars, we will use a two-phase approach. In Phase 1, an ecosystem of 3D printing robots will arrive months in advance of any human explorer. They will construct a protective shield for the base by adopting a modular robotic swarm strategy, a plan that allows for redundancies and enhances the odds for success. Intelligent autonomous robots will have interchangeable roles, from battery storage to scout rovers, logistics to excavational, and even 3D printing units, all integrated with multiple cameras and sensors for navigation. They can reconfigure themselves for a multitude of purposes, ensuring prolonged usage beyond the initial build phases. The smallest configuration is the one-wheeled Scout rover that uses ultrasonic scanning to analyze the Martian surface to determine the best regions for obtaining optimum regolith. The digger receives the location coordinates and then excavates the Martian soil. It then delivers the payload to the refining assemblies. Here, large chunks of Martian regolith can be processed down to a finer grain and then delivered to the melter robots in situ. They then use concentrated microwaves to melt the regolith and extrude through the 3D printing nozzle. The shell is autonomously 3D printed, layer by layer, over several months by the robotic system. In the next phase, the first astronauts arrive with the habitation units, equipment, and supplies. The robots now take on their second life roles to aid the next phase. They come together to make flexible mobile platforms that can carry the payload from the loading zone to the base. The convoy begins its journey across the Martian surface to the habitat site. The build commences with a connector module placed underneath the protective shield and readied for inflation. The module then unfolds and self-inflates into its final form. The habitation units are then placed into position and sequentially inflated to form the completed pressurized environments. The circular layout of the habitat ensures continuous accessibility of the habitat in the event of a catastrophic failure. Each connector module houses 3 integrated environmental control life support systems, delivering essential services like power, water, data, and oxygen to all the habitation units. A circular conduit delivers these services to multiple endpoints in each pod. The base will be remotely powered by 2 nuclear kilopower reactors and a solar farm, located a safe distance away from the base. In the next stage, the astronauts will construct and install a flat-pack, rail-based racking system capable of connecting to the distribution system, enabling spaces to reconfigure according to their spatial needs. This modular and radical design principle has been adopted for all the habitat pods, ensuring multi-use, reconfigurable environments. A Martian base should not just be a habitat. It is home for the astronauts. Each pod expresses its own identity, quality, and character. A highly functional design which places the human experience at the core. Spaces include a state-of-the-art research laboratory, a hydroponic greenhouse, a fully equipped workshop with digital fabrication facilities, the sleeping quarters with gym facilities, and immersive virtual reality platform. We believe that the key to success of human habitation on Mars is the health and well-being of its residents. Creating a place where work, life, and living combine holistically to ensure they feel connected to each other, to themselves, and somehow to their distant home.